So guys, you're welcome back again to a continuation of hydrostatics. And in the concluding part, which is the second video before we go to hydrodynamics, we are going to be looking at the remaining part of what we did not discuss in the last chapter. And the first one we have here is the Pascal principle, which is basically known as our law of our transmissibility. So another name for Pascal principle from early classes is given to be law of transmissibility. You can keep that at the back of your mind because you might actually need that in some situation. So about that, we can quickly write the law. The law was given according to Blaise Pascal, which I believe you've learned about in early classes. And so it's also known as law of transmissibility. So let's quickly close the law and we go into the practical analysis of some other things quickly so that we can understand the concepts well. The law, according to Blaise Pascal, states that the pressure applied to an enclosed fluid is transmitted equally. Pressure applied to an enclosed fluid is transmitted equally to every portion of the fluid, equally to every portion of the fluid and the wall of the containing vessel. So this is the law according to Blaise Pascal, and this is always asked in most of your questions to state. So you can keep it in mind that this pressure is transmitted equally throughout the whole bulk of the liquid. Now, from the first illustration we have, from the diagram we have in front of us here, we can quickly explain that from what we have learned before. Now, let's take this particular to be the height of the whole bulk of this. As we know that pressure applied at a particular point, we are considering that to be the height of the liquid, height h. Now, if we take any point inside the liquid, as in we are taking any point we want to take, we can take any of the points. What Pascal is telling us is that the pressure at any given point is always equal. So you can always put that at the back of your mind that whenever you draw and horizontal line within the layers of the liquid, and you are taking the pressure at each of the points of the liquid, the pressure at one particular point will be equal to the pressure at every other point. So keep that at the back of your mind. Please don't make mistake when you are doing something like that, because most of your question will test you on this particular thing I've just said. If I consider a point which I just ruled all over here, and I'm taking that particular point and I want to get the pressure at that particular point. Now, let's say we have this point, I'm taking point A, point B, and point C. According to Pascal, pressure at A, which we write as PA, will be equals to the pressure at B, which is PB, and will be equals to pressure at C, which is PC. So from illustration 1, we can say PA is equals to PB, which is equals to PC. So pressure at any point is always equal. So far, you are taking the point in an horizontal line. So that is what you need to understand, because force is acting at different points. So what we are trying to say is that the force at a particular point that is taken horizontally, this is the direction of pressure, is always perpendicular. You understand when I say perpendicular? That is normal. So I've explained that in the first video. So pressure at any point is always what? Equal. So far, it is taken on the same horizontal line. And from what we have studied, this should be a transparent diagram, but nonetheless, we can still understand. We said there is another type of pressure that comes from the atmosphere we call pre-atmospheric. So we want to get the total pressure from our last lesson will be the sum of the atmospheric pressure plus the normal pressure. Now, similarly, we can also bring another fact out from what Blaise Pascal was trying to tell us from Pascal principle. Is that pressure is transmitted equally to every portion. That is, the pressure at one side is equal to the pressure at the other side. And because of that, we also need to be careful about the concept of understanding that the pressure, we can put this down, another important fact, the pressure in a fluid, depends on the height. So that's another important fact you can keep in mind. That is, the higher the height, the higher the what pressure. So now, if the height of a vessel is increased, the pressure tends to increase. So direct relationship, before we have studied that pressure is given as H rho G. Remember that? So what we are saying here now from Pascal principle is that pressure depends on height. That is, pressure is direct proportional to height. That is, pressure as you go higher, the pressure tends to increase. So these are simple things you can keep in the back of your mind. And if you want to relate equality sign, you can bring a constant of proportionality, and you have P1 over H1 is equals to P2 over H2. Be very, very careful that when we say, another important point, which I want to also talk about, is that the pressure of a fluid, do not depend on the shape of the container. So this is another thing we can also conclude from Pascal law, which I'm trying to break down in simpler form or simpler fashion. So keep it at the back of your mind as well that no matter the shape, whenever you take a line, let's fill this with a liquid, for example. Let's just do that first. So if we fill this with a liquid, as you can see, to any point, maybe it is filled with liquid. You can see the shape of the first container is not the same as the shape of this now. Just trying to show some illustration for understanding's sake. So let's say this is filled with liquid. The liquid is here. Now, then we are taking a particular point as discussed inside that layer. Now, in as much we are taking the point here, like what we've talked about, the pressure at each point is still always going to be the same thing. And that is what we have been talking about. So pressure at the point here, we call point A. We take another thing, this is point B. Can take another one here at point C, will still be equal. So no matter the shape, in as much we are taking an horizontal line within the layers of the flow of the liquid under a particular height, the pressure is always the same and it is distributed evenly to every portion. So regardless of the shape, pressure liquid pressure or say fluid pressure do not depend on the shape of the container. So be very, very careful about this. So you talk about area does not have any effect on fluid pressure. So that is the meaning of this. So keep that in mind. Area has little or no effect on pressure when it comes to fluid pressure because it does not depend on the shape of the container. So this is the definition of Pascal principle, and we have its applications, which we are still going to talk about as we move on in the next slide. So the area of the container, it's also the same thing as what we are talking about. So the area, cover, the shape, the construction does not matter. The only thing that matters, I have explained in the last video that if I have a different liquid that is placed, the rest assured that maybe for example, for an instance, I have something like this, a U-tube like this. And in the first one, I have a particular liquid that is filled up to a particular level. Let's say to this level now. Then the second part, I have another type of liquid, which I will illustrate by dots, just for understanding's sake, for us to understand this. As in, I have different liquids inside this now. So if I draw a straight line, which is our vertical line that we've discussed here, the pressure at this point A, and the pressure here, we call it pressure at point B. You should always keep it in mind that pressure at A is not equals to the pressure at B. And the reason is because there are different liquid inside this what? Inside this vessel. And we've explained that talking about gauge pressure, and when we fill in a gas in the YouTube in the last lesson, which we talk about the total pressure acting will be the atmospheric pressure plus pressure at that point, then added to the one that is coming from the gas. So all these we've discussed. So with respect to this, we can talk about more application of Blaise Pascal principle, and we can do that in the next slide. So let's quickly check that in the next slide, and we have fine. Now, one of the application of Pascal principle is the hydraulic lift or the hydraulic press or the hydraulic forces. Now, because we have studied, so it's an application. So we can say application, one of the application which I'll quickly talk about is the hydraulic forces. Now, forces exerted by a body. We know pressure is force over area. We've discussed that time and time again. In the introduction, force is a vector quantity, and this is area. So one thing we need to understand is that when we talk about the direction of force, the force is always equals to the pressure multiplied by area. That is just cross multiplication of what we have here. So force acting on at a particular point is always equals to the pressure multiplied by the area. Please, I have told you also not to make mistake between forces, between our pressure and density. You know, density is also something like this, what we call that rho. So these are very important. So my point here for us not to make mistake is we must be able to identify the direction of force. Now, remember in the previous slide, we talked about when we are talking about the pressure that acts on an horizontal layer, the pressure is always the same, in as much the liquid there is the same, because it acts in all directions at an horizontal level. I have done some videos on this also. You can watch that. That's a classroom video, one of my old recorded video. So when you take an horizontal line, the pressure at that horizontal point, at that point, any point you take inside the layer of a liquid, as I'm trying to illustrate here now, I draw an horizontal line, forces are acting in different directions, because we need to understand concept. So as forces are acting in different directions, if you take horizontal line, we say the forces cancel out each other. Forces from left, from right, from up, from down, they come to meet at equilibrium, then they cancel out only in horizontal direction. But if I consider force in other direction, that is downward force and upward force. So one pressure can pull or push away the other. We've talked about that one in the manometer tube in our previous examples and previous video. Now, what we are trying to talk about here is that the effect of force with respect to what Pascal principle. Now, looking at this very carefully, not to waste our time, we have studied before. We have two forces acting in this diagram. We call the first one, and I call it my own so that we can see it. Let's say an inward force was coming here. We call that F1, just for understanding's sake, and an outward force was coming here, F2. It is not necessarily the hydraulic press must be like this. It can be in any way. I can decide to have a rough diagram also in which I have a small hydraulic. I just want to show you something that is okay. Can see this is another type in which this has a large area, force is coming. This has a small area, force is coming. So what I'm trying to say, this is direction of force, inward force. Out of it, you can say its direction is coming in, force was applied, also another inward force. What we are trying to say is that forces will balance out each other. This one is having a large area, we can call it area 1. This one is having a small area, we can call it area 2. As a result of equilibrium, what happens is what? The force will balance what? The other force. That is the pressure at one side is equal to the pressure. Pressure at one side will be equal to the pressure at the other side. So if pressure are equal, I'm telling you how all hydraulic lifts and hydraulic forces work. They work in the same manner. So if pressure is equal, so because pressure is distributed equally according to Blaise Pascal. So going by that, we can say pressure is same. So if pressure at one point, let's say the pressure at this point is P1, and the pressure at the other point is what? P2. We have studied that here. We are talking about the force over over a particular area. So we can say the first force here is F1 divided by the area here is A1 must be equals to the second force there. We say F2 also divided by A2. This is the way we relate all hydraulic forces or hydraulic press. This is the principle. Then we can say this is A2. I'm taking this as A1. So directly I can just make a F1 sorry a formula. It is not compulsory, just for you to see. F1 will now be equals to F2 A1 divided by A2. So this is conservation, and this is what we are trying to talk about now. If you watch very carefully from little things you can see here, from the diagram you can see, we can see that the amount of force, F1, small force, is here. You can see now, it is now used to push what? Something that is what? Heavy. So what I'm trying to say here is that you can say F1 here is now equals to the product of what? The F2 multiplied by the short area divided by the big area. So what we're trying to say now is that pressure is seen when it is transmitted inside a vessel, in as you can see. And what we are trying to relate is the force and area of one must be equal to the force and area of two. And this formula is very important for you to keep in mind. Either you know it like this or you know it in this way. It is very important to keep it in mind in case of numerical questions that asks about changing what pressure from one end to the other. So now we are through with this, and we can also look into the next thing we have to talk about before we start our illustration classes. Fine. Now the next one here is what we call the average pressure. Average pressure on the side of average pressure on sidewall of a vessel. The average pressure on sidewall of a vessel is what we have left. Now, and about this directly, we can quickly consider how to calculate the average pressure on the sidewall of a vessel by taking a cube, as you can see, and trying to use our knowledge of the integration, because we are only going to take an elemental part. When I say elemental, I mean a small part, and that is what we want to do. So now here we should just understand that I'm going to use our knowledge of integration to derive the formula, and I will only take one side. So let me just consider maybe this side. I just want to take an elemental strip. That is the way we do it. You can watch videos that explain the concept very well. So I'm taking this elemental strip, which is a short strip. The total height of this thing is keyboard as length, width, and height. So the total height is height h. We only want to consider the pressure that is acting on this side. So I will just consider an elemental strip and go by my knowledge of integration. So doing that directly, let's take something. Now we know forces will act in different directions, and because of the direction of force as studied, we are only taking this place. There will be a force. Let's change. The force acting at this will be the force acting in the outward direction. So I'm only taking a short height from here to here. I am not considering the whole height because I'm taking an elemental strip, STRIP. So what I do here is just taking the dimension of the height I want to take here is just I'm taking the y. So I'll call the height from that place to that particular point as the y, whereby the total height from here to here is nothing but I'll call the height from here y, sorry, and the one from here to here, which I'm taking as the y. So don't let us make mistake. And the total height there is h. Now let's go by what we have learned from previous slide. Now remember we say our pressure, I just take it calmly and slowly. Pressure is equals to force divided by area. Now, invariably, directly, I can say force is the same thing as pressure multiplied by the area. I hope you are following this. Now, I only want to take the force, the outward force, we can say it, in this elemental strips. That is the force under what? An height of y. And we've also studied that pressure, remember, is equals to what? H rho g. Remember that? Where h is the height, rho is the density, and g is the gravity. But in this case, I am not taking the height. My height here, I'm only taking the height of y. So I'm only considering the pressure at this particular point, elemental, small part, instead of considering the whole height of the cube or the whole height of the cubeboard, anyhow you want to call that. I'm only taking little part, and the little part I'm taking is what I have shown. So now doing that, I can say the pressure at that point will be the height of this thing. Now we are taking the height here as y, then we have rho and g. That will be the pressure that will act at that part of the cube. I hope you understand. So we said times area. Now, what is area? I will take it one by one for you guys to understand. Area is always equals to what? The area at this point, area of this shape is the length multiplied by what? Sorry, area at this point is, I'm taking only this side. I should have actually removed this compartment, but I want you to flow. So area is length times breadth, basically. So at this point, the area here is W, which is the width here, times the height. What's the height here? We are taking the height as the y. So the area there is what? W multiplied by the y. W here and the y here is like length times width. Width times length. Area is length times breadth, length times width. So for that shape, we're only taking that small part. So length of that is the width, which is the width, multiplied by the y. And that is what I have done here. So if I want the force that will act at the side of this vessel, we can now say the force from the formula. Therefore, we can move to black. The force here, that is the outward force, which I've shown at that point, will now be equals to, you can follow, the pressure. What's the pressure at that point? Y rho g multiplied by, what is the area at that point? That is W d the y. I hope you guys are getting this, and that is the first thing I have done. So now, at the whole part there, that means I want to calculate the total force acting at the side wall. So I can now say the total force. In continuation, we can write total force, the total force acting on side wall. Because this is the only part. For me to get the total force, I will just take a part out of the whole shape. And the part I've taken is that one I have drawn with that black. So now I want to take the total force at that point now. And if I want to do that, I am going to say the total force F total, I can call that FT. Now, whenever you want to take total force, you have taken an elemental part. Then for you to get the whole part, you are going to do what? Your knowledge of integration. So if I do that, it will now be integration of the elemental force. What is the elemental force? Y rho g W dy, taking the limit from what? What is the total height now from here to here is what? H. I'm taking the limit of this one from what? Is 0 to H. So keep that at the back of your mind, as this is the way we are going to do that. Whenever you want to take the area under a particular thing, you will use our knowledge of differentiation and integration to break such down. So without wasting time, let it be known to all students that the only factor that is changing here is what? Is the y. As all other factors here remain constant, because the y is the only thing changing. Every factor here, that is rho GW is what? Is constant, but this is what? Now let's integrate. Now from your knowledge of early classes, you know that if you integrate x will give you x squared divided by 2. You add 1 to the power, you divide by the sum of the power. The same thing is what I'm going to use here. Let me clean that. And directly what I told you is that every other parameter here is constant. Only y is what you are integrating. So doing that, go to blue, we have, it will now be, the value here we give us, we are taking limit. It will give us, if we integrate y is having 1 here, then plus 1. It will give us y squared divided by 2. We are taking the limit of y from 0 to h. Remember, every other parameter here, which are rho, please, you can always look at it. G and W remains what? Remains constant. And we are taking the limit of this one from what is 0 to h. What limit means is you are going to subtract when it is h, when y is equals to h, minus when y is equals to 0. So because we are taking it from 0 to h, we don't need to stress ourselves. When you take anything away from 0, it will still give you that thing. So by that doing, so where I see white, I'm taking limit. You can put it here for understanding's sake. I'm taking limit from 0 to h. So where I see y now, y is now h. So it will be h squared by 2, which you can write as 1 over 2 directly. Then we have h squared. As you can see, I'm using capital H, well, no problem. H squared, then I have rho GW. 1 over 2 H squared rho GW. Where is 1 coming from? There is an invisible 1 here, and there is also 2 under. So 1 over 2. How am I having H squared? If you are given 4x and they gave you limit from 2 to 0, because we are doing this for everybody to understand. What it means is that where you see x, you put 2. 4 times 2, 8. Then 4 times 0, 0. 8 minus 0. Answer will be 8. We don't normally do this 0 because the 0 we always make something to be 0. 0 times anything will still be that. In this case, we are having h and 0. Where we see why we are putting it, that is h squared over 2. Then the 1 of 0 is the 0. So it will go. So we have h squared over 2, which I have written as 1 over 2 h squared. So what we are trying to say is that the total force acting on the side of the vessel is now 1 over 2. I hope you are following. We have h squared. Now, look at this now. We need to know what we are doing now. Volume from early classes. Volume is always equals to, let's clean this side for clarification. Volume is always equals to area. I hope we still remember that. Volume is always equals to area times the length. So here, area times the length, or the whatever, the width or the dimension. You know, volume. Now, in this case, h squared W is the volume, because h squared is area. Area is h squared. I hope you are following. And W, this is not omega, this is W is the width. So when you say h squared times W is the volume, because h squared means h times h. Then W is what? You can even use dimension, meter times meter times meter. You are going to have meter cube. So what I'm trying to say here is that h squared W is now going to be replaced by volume. Then we are going to have nothing but what we have here. Please, we just need to understand that we have, it will now be P, we have P alpha, P, you can write it in another form, P rho, PG rho H squared. For understanding's sake, then I said H squared, H squared, H squared, and W is now volume. So I can change this one to volume. But similarly, this is the formula. If you are using this formula directly, you are going to get it. But you can also reduce the formula by saying average pressure. I think that will be better. Average, because we are looking for average pressure. The average pressure acting on sidewall. This formula here is for force. Hope you know. This is total force acting on sidewall will now be equals to Now, from what I have written here, pressure is force divided by area. So what is the force we have? Answer for our force is 1/2 rho G WH squared divided by area. What's our area? Area is H square, or you said WH, WH. That is area. Area is what? W times H. Area is not, volume is this. This is value of volume. Volume area is length times breadth. Look at it. W times H, which we use somewhere around here. Look at it. We use W there because we are taking elemental soup. Here we are taking the whole height, WH. Now, what do you know, guys? Something gets cancelled out. This gets cancelled out. This is H squared. One of it will go and remain 1. What we have now is what? Formula for average pressure of a sidewall is 1/2. We have 1H, H rho G. So students should keep this formula in mind, as it is a direct formula we are going to be using later in the numericals and some questions in our examination that ask for the average pressure on the side wall of a vessel is always equals to half of the total pressure. What is the formula for pressure? H rho G. Average pressure, H rho G divided by 2. Half of H rho G. So I just want us to now to derive formula because of some advanced question that may ask you to derive formula. But if it is not needed, if you are good with formula, the average pressure is always half of the total pressure, or half of the pressure, which is 1/2 H rho G. And that is what we need to talk about. We move to the next one. Now, about the next slide, we have fine. Now, about the next slide, we have Archimedes Principle and Law of Flotation. Now, about this, I know most of us might have studied this in our early classes, and the knowledge of what we have studied in early classes will be needed here to understand the concept of Archimedes Principle. But before we can talk about anything on Archimedes Principle, let us first write what the law states. About that, we can write that Archimedes Principle states that we have states, and I quote, I think it's better to quote directly, when a body is partially, or you say wholly immersed in a fluid, it experiences an upthrust. Which is equal to the weight of the fluid displaced, which is equals to the weight of the fluid displaced. Now, the law is telling us that when a body is partially or wholly submerged, it's dropped into a liquid, it will definitely experiences what we call a weight at which it will be submerged. The weight which we call upthrust, which is same thing as the weight of the fluid of the body itself that was displaced. Now, to understand Archimedes' principle, we are going to be considering water and bucket and talking about the amount of weight in which it is boiled, BUOYED, which you call the weight of the fluid displaced when it has been submerged into a liquid, and that is called upthrust. What we are saying here now is that the upthrust is the same thing as weight of the fluid displaced. Weight of the fluid displaced. So when you are asked to calculate the weight of the fluid displaced, that means you are calculating the upthrust force. So directly, we can quickly look into a good one here. Let's take let's consider a bucket, trying to draw out a simple bucket. Let's consider a bucket. That is filled with a liquid to a certain level. So let's say the liquid is here, or filled to the brim. Let me just say it contains a liquid, as you can see. Now let's say we have something like a cylindrical object. It's now dropped inside this bucket. So let's take a cylinder and drop it inside. So we have something like a cylinder. Yes, it's now submerged at a particular height away from this now. So we consider the height, and we want to use red for us to understand. Please, you can just follow through. It's not something you don't know. So this is this solid was submerged, was dropped inside this. So we say the liquid is having an height from here, from the top to the bottom here. The total height is h, which we have been using since morning. So, but the height of what was submerged, what you drop inside it, is having, let me say it's having let's use the height of this one to be L. I just want to use something, not that I'm first doing something spectacular. So now, because it has been dropped inside it, there will be a particular weight that will be displaced at this point when this thing go inside the water. So the weight that is being displaced when that solid is dropped inside the liquid is what we call the upthrust, and that is also known as what we call the buoyancy, because of advanced level students are buoyant force. So if buoyant force we act, we know force we act in different directions. At the middle here, we can take 2 points for understanding sake. We can take the point here. I'm just considering the point here and the point here. Now, force we act here because of the pressure. Force we act here in upward direction. The force on top here, we act in downward direction. Let's say the force acting in upward direction, we are taking that as force 2. The one acting in what? In downward direction, we take it as F1. Force we act on top of the liquid at the top and at the bottom. So now we are saying the total force that will now act on top here, which is the buoyant force, we call FB. I hope you are following, because it will displace a force upward. So there is also going to be a force at the middle, but I've explained that all the one at the middle will cancel out. When you draw an horizontal line on top of a fluid, you always expect the force to cancel out. Inward, upward, everything will come, they will cancel out. So that is why we are not taking the force at the middle. So we have force here, force here. As a result of pressure, because this one is going up, it will be greater than the one that is coming down. Everybody knows that. So we can say the buoyant force of this liquid, so buoyancy, which is upthrust, anyhow, buoyancy or buoyant force, buoyancy or buoyant force, will now be the difference between the two forces. We say the one going upward, that is F2, minus the one coming downward, that is what? F1. So let us quickly recall our formula for pressure. Remember, I told you pressure is our force over area. So let's consider each of them. Now, at this corner, I'm going to take a place. I want you guys to be attentive so that you will get this very well. Now, you know, pressure is force over area. We have already discussed that. Area. So if we make force over a formula, time and time again, we've talked about it to be pressure multiplied by the area. So we are considering 2 points. The one up here, point X, and point Y, which are the 2 points where we have the forces. So let's take the pressure at this upper point now. So from what we have studied, the pressure at point X, which is equals to pressure, will be equals to, we say, H over G. So be careful, because this vessel is opened. Because it's open, there will be an atmospheric pressure. We call P atmospheric. We talked about that yesterday. So P, the pressure at X here will be P atmospheric. Please listen. Plus the height of this from here to here at this point S is what? H rho G should be our pressure formula. You know that. But at this point, what we use as the height here is what? L. So my height here is L. Then rho rho G. That is the pressure at X. Now let's consider the pressure at Y, which is the whole container from the top to the bottom. So the pressure at Y will now be equals to P atmospheric, which is atmospheric pressure, plus the pressure of the liquid itself. Now we are considering the total from here to here. The height of here from here to here was taken to be h. This h is the height of this stuff that is submerged. So the total height from here to here will be L plus h. So h here will be L plus h. Then we have rho G. So what I'm trying to say here is that we know that we are taking the area of the whole container as area is A. Let's consider the area to be A. Now we know from the formula that force is equals to pressure times area. So let's put it out. So force here, F2, which is the one acting on Y, the value here is P atmospheric plus L plus H rho G multiplied by the area. What is the area? We are taking the area to be A. You know, force is pressure times area. That is what I have done there, my dear student. Minus the F1 pressure is pressure at this point. It will be P atmospheric. I'm just substituting values. Then plus L rho G multiplied by A, as force is equals to pressure times area. Pressure times area. Pressure times area. So this is what I have done here. And now to get our answer when we subtract, we now say the buoyant force, which is the most important thing, buoyant force, after subtraction of this parameter from the other one, as in when you subtract this parameter from the other parameter, you are going to have, what I have here is H, A, rho, G. You can try it out. Every other parameter will cancel out. You can see when you subtract, this is minus P atmospheric. This gets cancelled out. I don't want to be wasting time on what I believe we all can do. So now we have a pressure of the buoyant force will now be HA rho G. Now from early classes, area times height. Area times height is what? We said volume is equals to area times what? Times height. So directly we can now say, fine, the buoyant force, which I will call FB now, is now equals to H times height times A is what? Volume. That is V, rho, and G. So this formula is what my dear student need to keep in mind as when you are calculating the buoyant force, which is also known as upthrust. In ordinary level, upthrust is called buoyant force. Is called V rho G, whereby this V stands for the volume submerged. What does rho stand for, my dear student? The density. And G is what? The gravity, which is always constant. So keep this formula at the back of your mind. Whenever you are calculating anything that has to do with Archimedes principle and you are asked to look for the upthrust, you know the volume, then this volume can be the total volume of this. And be careful, in some cases, when the question asks or tells you that some part of this thing is submerged, that is why here it is standard as the volume, but in some cases it can be volume submerged. If half of this thing is submerged, that means it is not everything that is what? That is going down. Do you understand what I'm trying to say? So if it is just volume submerged, just say if 1/2 of it is submerged, it will be 1/2 of the volume. If the volume is 10, and we are told that only 1/4 of the body is submerged, it will now be 1/4 multiplied by the volume. Do you understand? Because what Archimedes states is that sometimes it can be partially and sometimes it can be wholly submerged. Do you understand? So it is not every time. So the formula does not change. The only thing that changes is just V rho G is the formula for upthrust or buoyant force. But the only thing that can change is if question tell you that some parts are submerged. So if I say 20% is submerged, how do you do 20%? 20/100 times the volume. So if the volume is 30 before, it will be 20% of 30. Do you get? That is other technicalities you could face. So we leave that to the next one, which is the law of flotation. About law of flotation, we can directly quickly do that one here because everything must be together. And yes, after everything is done, then we have the law of flotation. Let's quickly state that the law of flotation states that flotation law now states a floating body, floating body displaces its own weight, displaces its own weight on the fluid in which it floats. A floating body displaces its own weight on the fluid in which it floats. That is the grammar way of writing the law of flotation, which is an extension of Archimedes' principle. In early classes, you have studied about density, mass, and volume, as in density is equals to mass by volume, and also the concept of relative density. To understand this, we can quickly illustrate that also by drawing something that has to do like a bucket, but now it will be something like a cylinder, a narrow cylinder, which I just want to fill in something there. So it's filled up with water to a certain point. Explain the principle of law of flotation. They're saying a floating body displaces its own weight on the fluid in which it floats. So we fill this up to a certain level. Then an object is now dropped, is submerged partially. Let's say the object we are talking about is submerged partially. What I mean by that, this is the O level. You can say not all the parts of the object is what? Is submerged. Not every part is submerged. And in this case, that is where law of flotation comes in. We know we talk about the force that is acting on top of this liquid. What do we call that force? We call it the buoyant force, which we call upthrust. The buoyant force, as discussed here, the buoyant force FB. So the buoyant force we act on top of this liquid, and the solid that is submerged, we have a weight. Early classes, we have studied that weight act downward. So if we try to draw the free body diagram, we say the weight of this, let's turn that to what you can see. So the weight of this is acting in this direction, and the buoyant force of this is acting in this direction. So because of equilibrium to certain, we say the buoyant force, FB, we balance out the weight of that particular solid, which is W. Everybody know the formula for weight. The formula for weight is mg. We have just discovered derived the formula for the buoyant force. The formula of buoyant force, which is upthrust, is V rho g is equals to the weight, which is mg. You can also keep this in mind because when a body is dropped inside a liquid, we can always keep it at the back of our mind that if the whole body is not submerged, some of the parts will float, whereas some of them will sink. But what we are trying to say is that the weight of that body is equals to the apparent, what you call the weight at which the solid is at which it is displaced. That is, the upthrust is going to balance out the weight. Please get that so that you don't make mistake. That is why we are trying to let you know this. I know some of you might have studied some of these in early classes by cramming, but now it's time for you to know them. And when you see them in interpretation of questions, it will be easy when you understand the concept. So the next slide, we are going to talk about another important concept, which we talk about, the apparent weight of a body submerged in a liquid. The apparent weight of a body submerged in a liquid. Now, when we talk about apparent weight, we need to also let students know that weight of the fluid displaced when a body is submerged, remember, we call that the upthrust. Now, apparent weight, that means the final weight. When a body has been submerged into a liquid, then there will be a particular weight, we call the apparent weight, which possibly most of us call tension. Tension is defined, early classes, tension is defined as the force that acts in string or rope. Forces that act in strings and rope is called tension. So apparent weight of a body that is submerged in a liquid is the same thing as the tension of that body. So the body will have tension, which is always from class 10. That is SS1. You are told that tension always acts away from the connection of two bodies, away from the point joining what a body. Tension don't act in the same direction. It acts away from the point of contact. This is the way we define tension under Sykes' Newton law of motion when we learned about the free body diagram, or those of us that are doing A-level questions and stuff. Now, what I'm trying to say here is that to get the apparent weight of a body that is submerged in a liquid, we are going to consider using a spring balance. So I can quickly first of all write that apparent weight is also the same thing as the tension. So to understand this very well, maybe I should also take another illustration, which I think I need to draw for you to understand very well. I have diagram not drawn to scale, just manage my diagram. I'm just trying to bring out something. I know some of my students are laughing already, but it doesn't change anything. I'm just trying to bring out something like a spring balance that has a dimension measured in kilogram force and is connected to a spring. Like I said, diagram not drawn to scale, and we have a mass, a block of mass, usually of mass M. This is a spring balance that is going to read this. Now, from early classes, we have learned at the weight of this thing, we act downward. A bit of the load, we act downward. The load, I'm using it as mass M. Then the tension, we act against a bit this in upward direction. As a result of equilibrium, we can conclude that therefore, the tension here will balance out what? The weight. So we say the tension here is equal to the weight. Everybody knows formula for weight, which is always equals to mg, right? So here we can just say, fine. We measure, when you measure something, this is a spring balance that is used to measure. So it is always measured in kilogram force. When I say kilogram force, I hope you guys understand what I mean. We measure, whenever you are weighing something on a spring balance, it is always measured in a kilogram force. So please note that this is the unit, the standard units we use. Though everybody knows weight is measured in what do you call it? Weight is generally measured using a spring balance. We know that, and the CGS, the SI unit of weight is Newton. But I told you when you are using a spring balance, measure with kilogram force. Under the concept of forces, lift, and elevator, we have studied this, and I believe we still have it. We still remember all this stuff. And if not, we are here to understand it now. Now, this is the first case. Now, let me now make it a little bit of what we want to talk about. Now, in this case now, let me now connect this thing. Case 2 now, let me connect it. Let me bring a bucket here now. Diagram not drawn to scale. So let's bring in a bucket, and let's fill the bucket with water, black water. So we fill the bucket here with water, as you can see, up to a certain level where the mass, I am dropping that load, that mass, I'm dropping it inside, as in I'm submerging. That is the grammar we are using. So we should understand this, because that is what you will see in your examination. So I'm putting this mass now. It's now being submerged inside this. Remember, on top of this thing, what happened? Buoyant force. Remember, which we act on top. Now, if you watch very well, buoyant force is now acting on top of this. Now, the total force acting on for case 2. Let's write this as case 2. For case 2, we have two things for equilibrium now. For equilibrium to set in now, just like what we did in case 1, equilibrium. Yeah, watch, so that you get it. For equilibrium to set in now, we say upward force must be equal to the downward force. Then the upward force here is what? Two forces are here now, which is acting on top of this liquid now. We have what? The tension and the what? And the buoyant force. So you say we have tension plus the buoyant force, FB, must be equals to the weight, which is acting downward. Remember, buoyant force, you can write it as upthrust. So you can also write it in your own way as tension is equals to tension plus upthrust. Buoyant force is also called upthrust. Tension plus upthrust, look at me. Sorry about that. Tension plus upthrust is equals to weight. So what I'm trying to say here is that we can now say, okay, fine. We can make tension subject of formula, which everybody should be able to do, by saying tension is equals to the weight minus the upthrust. Now, from what we have studied, we know that the weight is equals to what? Mg. And the upthrust is equals to what? V rho G. So we need to understand this very well. Another thing we need to understand that there are different density here. The liquid has a density of rho L. The solid, you can see that this is a solid. We also have its own density. I'll call it rho S. Excuse me. Why am I doing that? You can use this formula directly as formula for tension. No, tension is equals to mg minus v rho G. It's very correct. And this is even another thing you can always keep at the back of your mind, that when a body is going down, that means the weight downward is what? Is bigger than the tension on top of it. So when the weight is bigger, is greater than the tension, you can say the body will sink. That's what I'm going to write down for you, because that is also very important in some non-numerical question. When weight, you can see the direction of weight is coming down. Where is tension? Tension is up. So when weight is greater than you can say apparent, what we're talking about here you can see we are talking about buoyant force, which is the upthrust. So when weight is greater than the upthrust, the body will go down. Weight is coming down. So body will sink. Just for us to have that at the back of our mind. Body will sink. And when weight is less than upthrust, which another person can write as when upthrust is greater than weight, what happens to that? Body will float. So this is another thing in continuation to the law of what? Law of flotation and the apparent weight of bodies. So the formula for the apparent weight we call the tension, is now equals to, you can keep this formula in mind, it's very important, and we are going to be using it directly in some application. But for A-level students, most of your numerical question will come in this way. Now, remember that volume submerged. Now, let me show you another thing in continuation to the formula. Volume submerged, volume from density, rho is equals to mass over volume. Everybody should know this. So volume, if you make volume subject of formula, volume will be equals to mass divided by density. The density we are talking about here, what are you submerging? Is it not the solid? You are submerging the solid. And because you are submerging the solid, so it will be this. So volume is mass over rho S. What does rho stand for? Density of solid. So we can continue and say tension, which is what we call the apparent weight, is now equals to mg minus, what is volume now? Volume is mass over, so you say mass m over rho S multiplied by Rho, this rho is rho L, that is rho of the liquid, rho L multiplied by G. From what you might have studied, you can rewrite this equation as tension is equals to mg, please watch, minus, I have m here, rho, I can write this one, this is m and g are also here, this is m times g is going to give me mg. And I have rho L over rho S. I hope you can see this. And I hope you understand how I come about this. And if not, I can quickly take that again for you to see. I have, from this equation that I have here, this is mg, m times g here is mg. We open a brief bracket. What is here? Rho L. What is under? Rho S. So you can also factorize. Tension will now be equals to mg is common, mg, then mg times what will give you mg times 1 minus rho L over rho x. This is rho and not pressure. Rho is density. So this is the formula you need to keep in mind to calculate the apparent weight of a body submerged, which is called the tension. So next time you see apparent weight, tension is always equal to the weight minus the buoyant force. What is buoyant force? The upthrust. What is weight? Mg. What is apparent weight? Tension. So what relates tension, weight, and buoyant force, which is upthrust, is tension is equal to weight minus upthrust. And the tension formula is given directly as mg open bracket 1 minus rho L over rho S, while rho L is density of liquid and rho S is density of solid. Students should be careful not to make mistake by directly, either you have the formula like this or you have it like this. Both are valid, but this is more valid depending on the nature of numerical. But most numerical in JUPEB and IGMB, we ask you direct question with respect to that. So guys, the next one should be what we call the illustration part, which is the concluding part of all what you have learned. And during the illustration part, we have illustration questions are next. And directly for illustration questions, we have 2 per page. Like I do tell you, you have to do more practice because practice make perfect. So you have to practice more. When you practice more, there are still more questions. I'll be taking this question with respect to what we've learned. At the end of every chapter, this is the way we do it for our new series of videos, which are available for download. Now, the first question on illustration today is, like I said, don't forget, I am not the one that always prepared this illustration. They are prepared by some of my good students that have learned a lot, and some of them are already in tertiary institution. And that is why when you see some questions, it might not be of your level, but don't worry, I will help you break them down for better understanding. So we have which of the following statements about liquid pressure? Liquid pressure is the same thing as fluid pressure that we have studied. It's not correct. The question tag here is that we are looking for the one that is not correct about fluid pressure. Remember, we've studied Pascal principle. Now, they said the pressure at a point in a liquid is proportional to its depth. What does depth stand for? Depth is height. Remember Pascal principle? We said pressure is proportional to height. So this is valid. Second one says, at any point in a liquid, that is the pressure at any point in a liquid is the same thing as the same level. When we take an horizontal line, the pressure at any point in a liquid is always what? The same. Valid, right? Fine. The third one is what? Pressure is exerted in all directions at any point. Yes. At any point, pressure at one point will be the pressure at other point, will be just like what I explained now, in as much they are at the same horizontal point, and they are not containing 2 different liquids. I hope I'm communicating. The next one says, this is also valid. The next one says, the pressure of a liquid at any point on the wall of its container acts in all directions perpendicular to the wall. Direct formula, direct quoting that we have quoted. Pressure acts normal. Normal is what? Perpendicular to the direction. That is why when we take the height and we draw a straight line, pressure at that straight line, that is normal. You know what I mean by normal? Perpendicular line is always like this. This is the height, And this is the pressure that you are taking. You know, pressure at this point is equal to pressure at this point, is equal to pressure at that point. So pressure acts in all directions. Pressure applied to an enclosed fluid is transmitted all equally, undisturbed, to every portion of the fluid. So it is always normal. The direction of pressure is always normal to the wall. Please note that it's always normal. And pressure at this point acts in all directions. The force will act in all directions, and they will cancel out each other. We've talked about that. It's also valid. And the last one is what? The pressure at a particular depth depends on the shape of the vessel. In fact, if I had known that this is there directly, I don't need to take you through this. I would have actually gone to that, because we talked about that directly under our Pascal principle, that pressure do not depend on what are on the shape. So whenever you take an hypothetical line normal to the direction of the height, the pressure is always going to be the same and does not depend on the shape. So keep that in mind. The answer to this is choice E. This is the answer to that. And pressure does not depend on shape of the container. The next one is illustration 2. About illustration 2, we have which of these statements are true of pressure in liquid? Still on Pascal laws and Pascal principle, law of transmissibility, Pascal law. So about Pascal law, we can say, fine. Roman figure 1 says pressure acts equally in all directions. It's valid because we've done something like that not quite long. We say pressure acts equally in all directions. Pressure decreases with depth. Is that correct? We say pressure depends on height. So when you say pressure decreases with depth, it's very, very what? It's very, very wrong. Pressure increases with depth. As height increases, what happens to pressure? Pressure tends to increase. So this is a wrong statement, because pressure varies directly with that. It does not decrease with depth, but it will increase with it. Depth is height. So pressure at the same level of liquid is the same. We talked about that up here. It's also very, very correct. The next, pressure is dependent. Dependent means depend. Pressure is dependent on the cross section. Does pressure depend on the area? No. It does not depend on the shape, which we talk about the area under our principle. So this is also wrong. So what do we have? We have 1, and what is this? And 3. Let's see the option. 1 and 3. This should be 1 and 3, because it's not 4. But my eyes is saying 4. It's 3. Oh, fine. So this is 1 and 3. Option A is valid. I would have said maybe the student that prepared the slide was sleeping on bike when he was doing that. So guys, that is the answer for the first illustration. We move to the next illustrations in the video. Good, fine. We have a good illustration about this is that we have a manometer, which we have discussed in our previous lesson, but it was not discussed here. I don't know why my student is trying to bring this slide for us to solve. For all the same, let's quickly solve that. We've talked about this time and time again. We have when one arm of a YouTube manometer, not YouTube that I always ask you to watch anyway, is connected to a gas supply. Fine. The level of mercury in the two arms the level of mercury in the two arms is slipping on by. He's writing it again. The level of mercury in the two arms of the U2 are as shown in the diagram below. Fine. If the atmospheric pressure is 76.0 centimeter of mercury, the gas pressure is that. Now, we've talked about this in manometer tube, and how we use it to measure the gas pressure when a gas is supplied. Look at that. This is going to be open. And because it's open, remember this, my dear student, atmospheric pressure is going to come here. So pressure is acting on top of this. So we can see, look at the direction of flow. I don't even know the way it's showing us this. The total height of this thing is 13.4. But look at the gas. There are two liquids. So you need to be careful. It did not draw this thing to scale. This particular liquid must be up to this particular line it drew. So please, for you to understand well, let me let you know. Now, the gas is having, let's say, pressure X, according to what I have explained to you. You can see it starts coming, pressure is the same up to this particular level. Please note. Then the amount of one that is coming, P atmospheric, is coming from here. I hope my students still understand. So we say the total pressure that is coming inside this liquid, you can see is flowing like this, will be equals to P atmospheric plus what? H rho G, already discussed. So now, which will now be equals to the amount of pressure that will act here. So the amount of pressure of this gas here that is coming to this point will be the amount of atmospheric pressure coming from here plus the pressure acting within the layer of the liquid, because it was, I think the gas is flowing outside. So if it is flowing like this, so we need to understand another important thing. We are told that the height of the whole thing here, the height from here to here is 3.5, and the height for the whole thing here is 13.4. So we need to calculate the remaining height from here to here so that we know what we are doing. We need to be careful. So the question asks that the gas pressure is, we are looking for the amount of pressure at this point, which I call the gas pressure, I call it PG. So from what I've said, if we want to get the gas pressure, that is knowing the total amount of pressure that will flow from here to this point. As in, the pressure that will flow from here to this point will be the gas pressure of this. So be careful about that. So atmospheric pressure is coming plus H rho G. So it's just that the way this diagram is drawn was not drawn well, but all the same, we can still get the interpretation. So H rho G, which is the height, then plus atmospheric pressure will be the gas pressure. So I can say the gas pressure, which is PG, is now equals to the atmospheric pressure coming from the atmosphere plus H rho G, which we say pressure depends on what? On height, right? H rho G is now what I'm taking as height. So directly I can say the pressure of this gas will now be equals to atmospheric pressure is 76 plus the height of this stuff will now be, so therefore we need to be careful about this. The H rho G, the amount of pressure only within this point, only within this. So like I said, he has only shown us the gap from here. His arrow here should be the distance from here to here. So we need to get the remaining distance from here to here. Everything is 13.4. I hope students are getting this. And here to here was what he showed. So this arrow should have been here is 3.5. So the remaining height here will now be equals to, that will be 13.4 centimeter minus 3.5 centimeter. So we need to do that. What's 13.4 minus 3.5? So that should give us something like this should be 10.5, but not 10.5. That is 9.9, I guess. Please confirm that. We have very good. That should be 9.9. So what we have should be 9.9 if it is correct. Yeah, 9.9. Then we have 76 plus 9.9. I hope it's in centimeter. Very good, 9.9. So 76 plus 9.9 will now give us 85. Okay, somebody is showing me something there. 85.9. So 76 plus 9 is 85 anyway. It goes without saying. 85.9 will be the pressure of the gas, which is in centimeter of mercury. So please put that at the back of your mind. And that is how we solve questions like this. So hope you understand what I have explained, because you need to get it. No, though we've done the concept under the manometer tool, now it's just for us to understand how to do it. Then the last question for this illustration video is an object of mass 400 gram, be careful about the SI unit, and density 600 kilogram per meter cube, is suspended with a spring, so that you can see that's concept of apparent weight, because it has been suspended with a spring balance. Those are ways to know what the examiner wants to ask you. So that half of it is in mass. You can see not everything is in mass. Conditional statement, half. Either you see half or 1/2. 1/2 is the same thing as half. Be careful about that. Is immersed in paraffin of density. Paraffin is what? Liquid. The solid is what? You can see, so that when you want to use direct formula, you know how to use it. So of density 900 kilogram per meter cube. The tension, what is tension? Apparent weight. We have studied that the second page, that tension is equals to, remember, the weight minus the what? Upthrust. Tension, which we call apparent weight. Weight is mg, remember that, And upthrust we say is what? V rho G. So directly we can use this and solve. So tension is equals to mg minus v rho G, and which we also remember the final formula if you can use that as well. But why I don't want to use that is because the volume submerged is not the whole volume. How much was submerged? How much did it drop? Only half of it. So half of the volume that you are going to get is what you are going to use as V. I hope you understand it. That is why practice question will help you. So directly I can just say, fine. So if our volume submerged is half, you can say volume submerged. What are you submerging? The solid. You are not submerging liquid, though. You are dropping a solid inside a liquid. Concept of early classes. So volume submerged, volume is equals to mass over density. We've talked about this before, over density, which was the way we derived the final formula, which was coined from this. Do you still remember? Where I say mg open bracket 1 minus rho L over rho S. We can use that directly too. I just want to do it elementary way. So we say mass of the solid. What's the solid mass? I will convert it to what? To gram. 400 to kilogram. Gram is the same thing as 0.4 kg. I hope students are here. So we have 0.4 density of the what? Of the solid. The density of the solid we are talking about is 600. So we are dividing 4 over 10 divided by 600. So what do we have, guys? We have we can do that one on ourselves, and we can also punch our calculator is allowed. That's 4 over 6,000. And 4 over 6,000, please show it well. We have 4 over 6,000 is what? So we can say 115. So I can just do it like this. Then remember what I want to say. The question say half of the volume. And that is the technicality. So we can say half of the answer we have here. It's the same thing. Why am I doing that? Because I told you when I was doing concept video that we follow the line of the question. Half of is 0.4 divided by 600. So which is saying that you can say is 0.4 divided by 12. Just trying to make it simple and direct so that you can punch your calculator in JUPEB or any form of examination here. We allow you guys to use calculator because it's theoretical. So now we can say, of which you can also do that 4 over 10 divided by 12, that's times 1 over 1200. Here 1, here 3, 300, 1 over 300. Anyhow you want to do it. We same thing as final answer. I can also use calculator. Let me punch my calculator. So we have 3.333 times 10 to the power 4. So let's see, object of mass 400 divided by 1000, 0.5. I'm trying to confirm. We are dividing that by 600. Then we have this. Then it was now in mass. So the weight of this thing is we have this is the mass as mg. We have 4 times g is always 10. Let's follow the line of what I'm solving. G is always 10. Mass is 0.4 times 10. That is 4 minus. Let's do everything here. This is the volume submerged. Please, I will still leave it like this. I'm leaving it at 0.4 because I hate long value in calculator over 1,200. Hope students understand how I come about this. I'm multiplying by the density of rho is density of the liquid. What's that? Times 900 times 10. I hope students follow this. So directly I can cut. I love this. This will get cancelled out. Then I have, we can cut as well. 3 can go for those that are good in cutting. 3 can go. Please, calculator is allowed. You can use a calculator directly. 3 can go here, 3. 3 can go here, 4. 0.4 divided by 4 is 10. You can do this. You can see 0.4 divided by 4 is 10. You can confirm that. I'm doing confirmation because we must get accurate answer. 0.4 divided by 4 is 10, even though I know it is should be 0.1. So you can see 0.1 times 10. You can see what I'm trying to say. This everything here is 3. But for those that don't know how I come about 3, everything here is giving me 1. See, 0.4 times 10. 0.4 times 10 is 4. 4 divided by 4 is 1. So I say this, cancel this, cancel this. Please use calculator is allowed. So what I have left here is tension, which is the apparent weight. Weight displays apparent weight is 4 minus 3. Then 4 minus 3 is giving us 1 Newton, which is the question answer. Please, if you have issues with this, I told you, you can send me a mail to me. You can send a mail to me and I will attend to you. In as much, I will send the answer to your mail and I'll help you break it down. But for this, I don't think this is a problem. But for those of you that love calculator work, why I refuse to use what I have on my calculator here is because it is the values are too long and whatever. But if you use calculator for all these things, V, O, G, but don't make mistake, please, because it's only half of it. So, and I told you just half of the volume. If it is the whole volume, you don't need to do anything. You just use it directly. So I have calculator here, but I don't fancy it. That is why I love cutting so that I will have what good answer. So that is the answer to that one. So please keep that at the back of your mind. This is where we are going to stop for this section of the part two. The next section we talk about hydrodynamics, where we have a lot to talk about viscosity, static truth, the Bernoulli equation, and so on and so on, Stokes law, Pascal equation, and the rest. So I'm just looking at how many videos I'm going to do for that. Maybe 3 as well. But see you soon and do have a wonderful time. Bye for now.